Hello students, we have come to the final topic for our physical chem series on electrochem. Yep, I hope you do not feel a little bit abrupt because for the past few months we have been dealing with organic chem, all the way from halogen derivatives to alcohols to carbonyl compounds and then carboxylic acid and derivatives and nitrogen compounds. Yeah, I think it is the right time to put this topic right at the end because right now you are dealing with a lot of transition metal chemistry and you're dealing with this displacement kind of reaction and a little bit got to do with reactivities, etc. So I think putting in electrochem now makes a bit more sense because I think number one, it is infamously known by your seniors to be quite difficult. Quite physics-like because you might want to revise a little bit about what you have learned from electricity from your secondary school chemistry, but not to worry, you do not need a lot of those knowledge. Yeah, but if you can, revising a little bit of that helps. And then of course, number two, as your intellectual capacity matures, you are now at the right moments to tackle these difficult topics. Yeah. Before we go into looking at the two broad topics, which is on electrochemical cell, largely known as batteries, okay, and electrolytic cell, which you are familiar with from secondary school. Maybe let me bring you through down memory lane on what you have gone through in secondary school. So I'm going to open up the O-level chemistry curriculum. Okay, so I'm just going to show you the O-level chemistry curriculum, which some of you might be familiar with. Even for students who came from the integrated program, most of what you have learned from the integrated program is largely similar to what your friends learn from their respective secondary school. Yeah, so if you take a look at the learning objective for the O-level curriculum on electrochem, you'll notice that it largely focuses on this broad idea called electrolysis. Okay, so if you just try to recall things you have learned in O-levels or secondary school, you are largely dealing with, say, electrolysis of a molten ionic compound or aqueous ionic compound, or even you try to perform electrolysis on water. Okay, and you can just read through the whole thing if you wish to, although you don't really need to. So largely it's on a process known as electrolysis. Okay, so everything is on electrolysis until over here where we discuss electroplating of metals. Yeah, so electroplating is also a focus in A level. So please do not forget what you have learned in secondary school. Okay, and the last learning objective from the O-level curriculum, if you read it, describe the production of electrical energy from simple cell. Yeah, so this is the only learning objective from the O-level curriculum where the students are being introduced to electrochemical cell, where electrical energy is being derived from redox reaction, and this is essentially the makeup of a battery. Okay, so you can see that so many learning objectives, 3, 6, 9, 10 learning objectives, only one of it deal with electrochemical cell. Okay, so now let me just show you the A-level learning objective. Okay, if you look at the A-level learning objective, which is your curriculum 9729, right? Yeah, so this is electrochem. Yeah, you will notice that quite a bit of it is focusing on electrochemical cell, and then it is the back portion where we will be dealing with electrolysis, which not very different from what you learned in O-level, except for something else which we're going to talk about it. And for A-levels, we will be focusing a little bit more on the calculations for electrolysis. Okay, of course, electrochemical cell, there are calculations as well, but I'm just trying to showcase to you like what exactly is the key difference between what you learn in A-levels and O-levels when it comes to electrolysis. Yeah, okay, so you will be doing some calculation, but not to worry, these are quite straightforward calculations. Okay, and you can see that a large part of your learning objective from the H2 curriculum, your A-level curriculum, is on electrochemical cell. Okay, so we're going to look at A, B, C, D, and then E, F, G, H, I, and then in fact it goes all the way to here. Okay, somewhere here. That's on the fuel cell. Okay, it's the last few objective, like the relationship involving Faraday constant, which I will not go into details. And then after that, you're also going to have some calculation over here, and then as well as predicting the identity of the substance liberated from electrolysis, which is quite similar to what you have learned in secondary school. Yeah, okay. And then of course, the last learning objective in explain in terms of electrode reaction, industrial processes, anodizing aluminium. This is new. And then electrolytic purification of copper, kind of new. You might have learned it in secondary school, but it's good to repeat it. Okay, you do not need to know the technical details. Okay, yeah. So broadly speaking, I have kind of like gone through with you the slight difference between what you learn in secondary school and what you're going to encounter in A level. I hope that doesn't scare you. Okay, I will also move in to talk to you a little bit about the data booklet. Okay, the different sections as well. But I will not bore you with the details by going through with you every single sections, because I think earlier on I've done a video on an introduction to the data booklets. That was last year. Yeah, so I think my main objective is to maybe showcase to you section 1 as well as section 4 with the standard electrode potential and the redox potential. Okay, section 1 is not new to you, but there are some constants which I thought you should know where to find them, or you should know that they exist in the data booklet. So number 1, for example, the Faraday constant, which is 9.65 times 10 to the power 4 coulombs per mole. Avogadro constant, I think you know that from stoichiometry, it exists as well. So just know that you should be using 6.02 times 10 to the power 23, not 6 or 6.023. Okay, good to know the Planck constant as well. Okay, which exists, and also the electronic charge, which is negative 1.60 times 10 to the power minus 19 coulombs. Okay, other than that, I think the rest of the constants you should be familiar with. Okay, I'm going to straight away jump into the next section over here, which is on the standard electrode potential. Okay, I think at this point in time you might not know what's standard electrode potential is. Basically, these are standards that are measured against the standard hydrogen electrodes. Okay, it showcases the potential difference, okay, between the electrode reaction which you are talking about and that's of standard hydrogen electrode. Yeah, so in short, what exactly does it mean by electrode potential? Basically, it is the thermodynamic tendency of the ions in the solution to reduce themselves without any current flow. Yeah, so it is a thermodynamic parameter. Yeah, so just take note of it. Yeah, but I'm not going to details yet because the details will be covered in the lectures. But what I'm going to discuss with you about will be what you'll be given in these 5 pages. Yeah, okay, so under section 4, right, you will notice that there are 2 parts to it. That's 4A. One of it is 4A. For 4A, the standard electrode potential are being arranged in alphabetical order. Yeah, but do take note that alphabetical order is with reference to their chemical symbols. Yeah, like so for example, silver, the chemical symbol is Ag, argentum, which is derived from its Latin name. Yeah, but silver is spelled with an S, so technically silver shouldn't be placed here. Yeah, but however, we are making it convenient for you, so we are placing the standard reduction potential values according to the alphabetical order of their chemical symbols. Yeah, so this is a more comprehensive list. So you'll notice that it spans about 5 pages. Okay, all the way to here. Okay, so do take note that all the ionic states refer to aqueous ions unless otherwise stated. I think that has been yeah, and other state symbols have been omitted. And 4B, it's when the standard reduction potential is being written in decreasing order of oxidizing power. Yeah, so what do we mean? So we means that let's say fluorine, that means that out of the whole list, right, fluorine is the strongest oxidizing agent. Yeah, then I think from here, you might recognize that the more positive the standard reduction potential is, the stronger is the species written on the left as an oxidizing agent. Yeah, and that means that that particular species that have a greater thermodynamic tendency for it to be reduced. Okay, in the case of fluorine, to be reduced to fluorides, and then in the case of peroxydisulfate, to be reduced to sulfates. Okay, peroxydisulfate is something which you should be familiar with. Maybe not familiar, but you have encountered it in JC1 when we are dealing with redox, or maybe not redox. We are dealing with kinetics. Okay, it is the reaction when you add when you pipette a color solution, which is peroxydisulfate, and then you pipette it, and then you let it react with iodides, okay, with a fixed volume, etc. And then over time you slowly pipette out, because the reaction between peroxydisulfates and iodide is quite slow. Yeah, so you are just measuring how fast iodine is being produced. Okay, if you can recall that reaction. Yeah, so that colorless solution is called peroxydisulfate. Okay, this data spans 2 pages, so it's being arranged from the strongest oxidizing agent to the weakest. Okay, then obviously the weakest oxidizing agent, which is potassium, you will also notice that therefore the potassium metal will be the strongest reducing agent amongst the whole list. Okay, so that is roughly how you can gauge what is the difference between whether you are writing the species on the left or on the right, but that is not so important at this stage. Okay, yeah, so I think in most cases it is easier to just refer to the first 3 pages of data, because they are written in alphabetical order, unless of course when situation arises, then you might think that looking at the data where they are being written in decreasing order of oxidizing power may be useful. Okay, so that's just a brief introduction to some of the data which you have in your data booklet. I know I am jump starting it a little bit, because at this stage you might be thinking I have not even learned anything regarding electrochem, but now you're introducing me to the information and data booklet, and I seem quite lost, because the data seems they don't really quite make a lot of sense to me lah. Yeah, but I think it's not the first time you have seen these half equations, because I think when you're dealing with stoichio and redox, you would have used some of the half equations to help you perform the balancing. Yeah, the only thing you're unsure of is what do all these value means lah. Yeah, so I think earlier on I mentioned that the more positive they are, the greater their tendency to be reduced to the ions. Okay, so I think a brief introduction like this sets you up in a very good position to start off this particular topic. Okay, so we'll move on to the lecture proper. Yeah, so as mentioned, there are 2 broad themes: electrochemical cell and electrolytic cell. So electrochemical cell itself is a battery. So in itself, right, it will generate a potential difference because of chemical reaction. So if you are putting a light bulb through, then you expect the light bulb to light up. For electrolytic cell, basically we are dealing with electrolysis. So you are using an external power supply to drive otherwise non-spontaneous reaction. Okay, so from what we understand, electrolysis of water to give us hydrogen gas and oxygen, and electrolysis of molten sodium chloride to give us sodium and chlorine. Yeah, because in most cases, sodium chloride will not break out on its own to give us sodium and chlorine. Whereas if I subject chlorine to sodium, it will react spontaneously to give us sodium chloride. Yeah, so that is why for a process that is non-spontaneous, we need an external power supply to drive the forward reaction. Okay, and earlier on, while going through the data booklet, I have gone through with you not every single objective of learning outcomes, of course, but just to share with you some of the learning objectives. Yeah, and you notice that the bulk of it is related to electrochemical cell, and there's a reason for it. If you ask me for the reason, because most of the stuff you have learned in secondary school are related to electrolysis. So that means that electrolysis is something which most of you are quite familiar with. So that is why for the A-level curriculum, we do not spend too much time on it. Okay, yeah. Then maybe just let me give you a very, very quick introduction. So basically, electrochem is the study of the interconversion of chemical and electrical energy. Yeah. And in order to generate the electrical energy, we are actually dealing with redox reactions. Yeah, and not just ordinary, not just any redox reaction, but redox reaction that are spontaneous. Yeah, so from the chemical energy of this reaction, we can actually utilize it and convert them into electrical energy. Examples will be batteries and fuel cell. And electrolytic cell is something which I have already discussed with you. So I think it needs no introduction because, again, as I mentioned in secondary school, you have encountered it. Yeah, but maybe let me just use a little bit of a space here to discuss or to just explain to you exactly what exactly is a electrochemical cell, and have we seen it before? Or I mean, of course, you have seen batteries, and you have been using your mobile phones and laptop batteries without plugging them into the external outputs, external power source, for the longest time. But I thought I just want to give you a slight historical background as to why scientists or chemists in particular are able to so-called utilize the redox reaction in order to so-called do useful work, like in that sense. Useful work in the sense to light up or to power up systems. Okay, so I'll just begin with a very simple example. So right now I'm just going to draw a vessel. So I'm just going to draw you a reaction vessel. So something like this. Okay, so I have a beaker. Okay, so in the beaker, right, I'm going to have copper sulfate solution. Okay, so basically just copper 2 plus aqueous. The concentration is not very important. So any concentration which you deem fit, maybe around anything between 0.1 to about 0.5 moles per dm cube. It doesn't really matter. And of course, copper 2, it can't exist on its own. So usually when you want to introduce copper 2 into the system, then you would expect sulfate as well. Okay, but sulfate essentially is just a spectator ion floating around. And of course, there's water as well because they are being solvated. Now, imagine that if I'm going to put a piece of, let's say I'm going to put a piece of zinc. Okay, I'm going to put a piece of zinc metal inside. Okay, so remember from secondary school, you learn about what we call the reactivity series. Okay, so if you cannot remember, let me just show you the O-level learning objective. Okay, I'm just going to go straight down. Okay, in the secondary school learning objective, if you recall from the metals portion, there's this thing called the reactivity series. Yeah, over here, the reactivity series. And I do believe that in secondary school, your teachers will give you some ways to go and memorize them in the reactivity series, right? Like the most reactive metal is potassium, followed by sodium, and then blah, blah, blah. And then any metal below hydrogen, such as copper, silver, they do not react directly with acid. Yeah, and then you guys have to go and memorize them. Yeah, and probably in secondary school, your teacher will probably not go into a lot of details like why is that the case, why is it that the element above can displace those lower. Yeah, it has all got to do with reduction potential and cell potential, etc. Okay, so so that's why in A level, right, we are teaching you more. You're able to do the calculation, and you will be able to predict whether a reaction will happen, say between a metal and the aqueous ions, the aqueous cations of another metal. Yeah. So in our case here, we understand from secondary school that from what you learn in secondary school that zinc is higher than copper in the reactivity series. Yeah. So if I'm going to put zinc in, just a piece of zinc, right? The portion it coming in contact with the aqueous solution, right? the zinc will go into the solution as zinc 2 plus. Yeah, so you are expecting a reaction to take place. So it will go into the solution as zinc 2 plus. Okay, and then copper will be deposited here on the surface of zinc. Yeah, the reason is because on the surface of zinc, there are electron density. So the zinc being more reactive than copper, right? The electrons on the surface of zinc will have a tendency to be transferred over to copper 2. So when it's being transferred over to copper 2, then copper 2 will become copper, which will stick onto the surface of the zinc plates. And then because there's an electron transfer, it's like a 1-for-1 exchange, right? So zinc will then be oxidized to zinc 2 plus. Yeah, so the overall redox reaction, which you will be writing, right, essentially is we are looking at zinc solids plus copper 2 plus aqueous. And then for reaction, I will be able to get zinc 2 plus. Okay, and the copper will be deposited. Yeah, so this is what you are familiar with in O level or secondary school. And to you, it's a knowledge because zinc higher up than copper in the reactivity series, so zinc will displace copper 2 in that sense. Sorry, not copper 2. And then copper 2 will be reduced to copper, and zinc will be oxidized to zinc 2 plus. Okay, yeah. So you realize that the electron is being transferred between the surface of zinc and the copper 2, which will surround the surface of zinc, because the zinc metal is submerged into the aqueous solution. Yeah, of course, scientists recognize that a reaction took place, and there's electron transfer. So but you notice that when the electron transfer just happened like that, right, we are not able to utilize the electron transfer to do work for us. To do work meaning we can't use the electrons to power up anything, because it is not going to travel through a distance, if you get what I'm trying to say, because essentially the electrons is just transferred between zinc and copper 2. Yeah, and they are transferred mutually. Yeah, so it's like a person A and a person B. If you imagine an electron is like a ball, so they are just throwing a ball at each other. Yeah, so the ball did not go through a distance to do useful work. Yeah, so what happens here is that scientists recognize this. So they try to change the system around. So they are wondering if I am able to allow the electrons to transfer over a wire. Of course, a wire with some resistance, and we try to use a voltmeter to measure. And of course, we can also put a light bulb there so that it can power the light bulb. Will we actually detect a potential difference between the 2 points? Of course, the answer is yes, they are able to do that. Yeah, and at the same time, you can use that to power up the light bulb. Okay, to light up the light bulbs. Okay, so what's going to happen is, instead of allowing zinc to come in direct contact with the copper solution, so what happens here is that I'm going to divide them into what we call the 2 separate half cells. Okay, so I'm just going to erase this. Yeah, so over here I'm going to have, instead of zinc, I'm going to have copper. Okay, and then I'm going to draw another half cell on the right hand side. Okay, sorry, I think it's not drawn very nicely. Okay, I'm going to draw it here, and then so over here I'm going to have zinc 2 plus. Oh, sorry, yes, 2 plus. Okay, and then I'm going to draw in the zinc. Okay, so this is zinc. Okay, so I'm going to connect them up, okay, with a high resistance voltmeter. Of course, the voltmeter is high resistance. Okay, and then I'm going to have a salt bridge over here to maintain electrical neutrality. Okay, yeah, so I need a salt bridge. Okay, so I'm just going to label this as a salt bridge. Okay, and because zinc is the more reactive metal as compared to copper, yeah, you expect it to be at a higher potential than copper. Yeah, so in that case, electrons will be flowing from zinc to copper in this sense. Yeah, and then so at any one point in time, zinc will have a greater tendency to donate electrons density or electrons to copper. Yeah, and what's going to happen here is that zinc being the more reactive metal, right? it will undergo this particular spontaneous reaction where zinc will be oxidized to zinc 2 plus. Okay, and you expect the zinc electrodes to decrease in size. So electrodes decrease in size, and then the copper will slowly be deposited over here. So I'm going to expect the copper to be deposited over time. Why is that the case? Because copper 2 plus will be reduced to copper solid. Okay, I think earlier on I forgot to put out the electrons. Okay, yeah. So essentially, I'm going to get a cell running here. And then how do I calculate the cell potential? Okay, I think intuitively you should be able to tell that because zinc is the electrode being oxidized, and copper 2 side is now being reduced, because the copper 2 is now being reduced to copper. Yeah, so based on the terminology of electrochem, we call the right hand side the anodes. Okay, because that is when the zinc is being oxidized to zinc 2, and then the left hand side we call it the cathodes, where reduction takes place. Yeah, so you should remember cathode and anode based on the processes that is taking place. Okay, so remember this. Yeah, so anode is when oxidation is taking place. Cathode is when reduction is taking place. And then right now I'm going to go to the data booklets. I know I'm jumping in quite fast, but let's just go to the data booklets. Okay, yeah, and then we just go and look at the data. Okay, so you can see that this is minus 0.76 volts, right, for zinc 2 to zinc, and then copper 2 to copper is 0.34 volts, right? Correct? Yeah. So in that case, later on you will learn that the cell potential, the standard cell potential, yeah, but in our case here, it's not standard condition, because remember earlier on, I did not put copper 2 and zinc 2 in the standard condition. What is the standard condition? The standard condition is, I think it's written, it should be written in your notes, 1 mole per dm cube for the aqueous solution, and then 298 Kelvin, and then 1 bar in terms of pressure. But it's not important at this stage, because later on we're going to introduce you again. Yeah, so we're going to calculate the cell potential, which is E cell. The reduction half cell, the half cell undergoing reduction, which is copper. So we are going to get 0.34, okay, minus off the half cell undergoing oxidation, which is zinc 2 zinc. So I'm going to get 0.76. Okay, so the maximum potential that we can generate from this particular system under standard condition is 1.10 volts. Yeah, so essentially we are having a battery here, because that is the maximum potential, that the maximum voltage that it can be generated. Yeah, so in case you forgot about your O-level physics or physics you have studied before, right? What exactly is potential difference? Basically, it is how much work that can potentially be done by the circuits. Okay, so if I'm going to replace the voltmeter with a light bulb, okay, so something like this, then it will light up. Okay, but of course, you need a voltmeter to measure the potential difference. Obviously, I mean, if you just have a light bulb, it just light up. You don't know the potential difference in that sense. This particular setup also has another name. It's a historical name. It's called a galvanic cell. Okay, so maybe it's good for you guys to know the historical name. Yep. Okay, so from here I'm just going to move away from the introduction. Okay, so the redox reaction, which is something which you are very familiar with, so I won't go into details. And then the reaction between zinc and copper is the exact reaction which I've illustrated to you above. Okay, so you'll notice that copper will be deposited on the surface of zinc. Okay, and then the two half equations, you can get them from the data booklet, or you can actually balance them quite easily. So I don't think it is any major issues. Okay, so I'm just going to skip this particular part. And when we are able to set them up in this particular format with a voltmeter connecting between the two electrodes, we essentially have set up what we call an electrochemical cell. So in this case, you expect electrons to flow from the cell with a greater potential to one with a lower potential. So it will flow from zinc to copper. Okay. I think that's about it. I don't think there's any other things which I have not discussed with you, but I will jump straight into section 2 on half cell and electrode potential. First, we need to understand what exactly is half cell. Yeah, so earlier on, when we show you this particular galvanic cell, right, or electrochemical cell, you notice that on the left-hand side, we have a zinc electrodes over here, and then we have the solution as zinc 2+. Yeah, so the zinc electrode will be what we call the reduced form, which is the native metal, and then the zinc 2 will be what we call the oxidized form. And then at the same time, on the right-hand side, we have copper, which is the so-called the reduced form, and then copper 2, which is the oxidized form. Yeah, so each of the setup on the left on its own and the right-hand side on its own, we call them the half cell. Yeah, okay, so we have a generic equations here being written for you, the oxidized form plus n number of electrons to give you the reduced form. And in quite a number of cases, to keep things simple at this stage, right, the reduced form tends to be the metal. But do take note, not all the cases. Okay, so maybe let me just give you examples over here. Yeah, you notice that the reduced form tends to be the metal, like for example, silver here, and then you have silver plus as the oxidized form, aluminum, and then aluminum 3+ as the oxidized form. Yeah, but this is not always the case, because for example, for iron, okay, I can have iron as the reduced form and then iron 2 as the oxidized form. I can also have iron 2 as the reduced form and iron 3 as the oxidized form. Yeah, so it is possible for the reduced form to be a to be the aqueous cation. It need not be the metal. Okay, then you'll be wondering, then in that case, what is the metal then? So the metal is therefore an inner electrode, which we'll introduce to you later on. Okay, yeah. So if I'm going to put in the piece of metal M with an aqueous solution containing M2+, right? Over some time, the M will attain an equilibrium with its aqueous cation. Yeah, so the more reactive the metal is, the more will the position of equilibrium lies to the left. Yeah, so I think that is something which you are familiar with from the concept of chemical equilibrium. Yeah, so let's say I have a relatively reactive metal. I mean, as I said, relatively reactive. I mean, it's not so reactive until all the metal will straight away react. Okay, so if I insert a piece of zinc rods into an aqueous solution, then you will notice that some of the zinc will tend to go into the solution, or will tend to dissolve into the solution as zinc 2. Yeah, and when that happens, right, you expect electrons to be built up along on the surface of the electrodes, or in this case, I think in our notes we wrote it as the zinc rod, or it's on the surface of the zinc rods. And then in that case, the zinc rod will have a negative charge, and then it will be surrounded by ions which are positively charged. In this case, it's zinc 2 itself. So a potential difference will now develop between the metal and its solution. Yeah, but it cannot be measured unless we measure it against a standard. And for most of our standards in H2, we are using the standard hydrogen electrode, which is, in short, we call it SHE. Okay, yeah, and then nickel being a less reactive metal than zinc, the position of equilibrium will lie less to the left, meaning that for nickel 2 reduced to nickel, as compared to zinc 2 reduced to zinc, so the position of equilibrium will lie less to the left as compared to zinc. Okay, then in that case, there will be a smaller build-up of electrons around the nickel rods, and therefore the potential difference between nickel and its solution is smaller. Okay, we can take a look at the data given to us from the data booklet. Yes, I know that you are not familiar with reduction potential yet, but just take a look at the values, and then I hope you can have some sense of magnitude. So for zinc 2 to zinc, you realize that it's negative 0.76 volts. Okay. For nickel 2 to nickel, you notice that it is negative 0.25 volts. So that means that the tendency for nickel to enter the solution as nickel 2 plus is lower than that as compared to zinc entering the solution as zinc 2 plus. Okay, why is that the case? Because the tendency for zinc 2 to be reduced to zinc is much lesser than the tendency for nickel 2 to be reduced to nickel. You notice that the more negative it is, the lesser the tendency for the species on the left to be reduced to the species on the right. Okay, remember earlier on we said that fluorine is the most powerful oxidizing agent known to man. It has a whopping reduction potential of 2.87 volts, which is the highest. Yeah, and then we are also agreeable that potassium in our list here, it has the most negative reduction potential. That means that potassium has a very strong tendency to be oxidized to K+. Okay, yeah, so I think you can use some of these values as a proxy to understanding the magnitude of their strength as oxidizing or reducing agents. Yeah. Okay, then let's see what we have here. Okay, so we need, as I mentioned, we need to reference it to a reference cell because the absolute electrode potential cannot be measured directly. Yeah, the reference cell will be the standard hydrogen electrode. There are other reference cell, but we do not introduce you to them at the H2 levels. Okay, yeah. So for the metal ion is very clear cut. Let's say we want to deal with non-metal, then what are we going to do? Yeah, so not to worry. If we want to deal with non-metal, then what we can do is we can have a chlorine-chloride half cell. Yeah, so let's say our oxidized form is chlorine, our reduced form is chloride. Okay, so there's a typo here, just chloride. Okay, so therefore we are going to dissolve some sodium chloride into the aqueous solution, and then for chlorine gas, we're just going to bubble it through using this particular apparatus. Okay, and then the electrode, we will definitely need an electrode. Please do not give me a piece of chlorine, there's no such thing. Yeah, so the electrode will be the platinum electrode, which is inert. Yeah, so this is something which I thought you could remember, and it will be good for you to learn how to draw this particular setup. Okay, and make sure that you have some holes here in order for the bubbling to take place. Okay, and then yeah, so this is the platinum electrodes which we are talking about here. So you just need to make sure that they vary a little bit in size depending on what you're dealing with. Okay, so over here you are dealing with bubbling gases into the reduced form, and over here, remember our earlier examples, we are talking about having both the reduced and oxidized form as aqueous metal cations. Then what are we going to use for the electrodes? Okay, so we are going to use the inert electrode, which is the platinum electrode. Yeah, so this inert electrode is not any different from what you encountered in secondary school or O levels. Yeah, basically inert electrodes are electrodes which do not take part in the chemical reaction. And platinum is one of the least reactive metal known to man. Yeah, so in that sense, it will only help in the conduct of the currents, but itself it will not be involved in electron transfer. Yeah, okay, so do take note, there's a difference between itself involving in the conduct of the currents versus itself involving directly into the redox chemistry. Okay, so there is a difference. Do not be confused by some of these terms. Okay, and the next section we are going to look at the standard hydrogen electrode, which you need to know how to draw it, because sometimes we'll ask you to just draw it out. Yeah, okay, so do take note of the standard condition which you need to be familiar with. Okay, so the standard condition will be hydrogen gas at 298 Kelvin and 1 bar. Okay, so that means that your hydrogen gas has to be introduced at room temperature condition, or rather 298 Kelvin temperature condition, as well as 1 bar, not 1 atmosphere, is 1 bar. And then earlier on, you need to allow some holes for the hydrogen to bubble off. And this is what we call the platinized platinum electrodes to increase the surface area. And do take note of the concentration of the H plus in the solution for standard condition, which is 1.00 moles per dm cube. Okay, and of course the wire here needs to be connected to a voltmeter, and of course you need the salt bridge to be connected to the other electrodes. Okay, so just take note of how to draw this. Okay, so I think you are given the information. Finely divided platinum on the surface of the platinum foil to increase the surface area, okay, for the redox reaction to take place. The solution is 1 mole per dm cube H plus. Okay, and this is known as the glass. This is known as the glass tube, okay, in case you want to know, or you can just remember how to draw the setup. The hydrogen gas has to be introduced at a pressure of 1 bar and 298 Kelvin. Okay, so basically, as long as you read standard electrode potential, the standard means 298 Kelvin, 1 bar, 1 mole per dm cube for the aqueous solution. Whether is it the cation or anion, just take note of it. Okay, what I really mean when I said 1 mole per dm cube is actually related to the either the oxidized or the reduced form in question, right? Okay, so next 2.2, measuring standard electrode potential. Okay, so I mentioned already the temperature has to be 298 Kelvin because this is the standard condition. So I think it will be good for you guys to remember it. Standard condition is 298 Kelvin. The pressure will be 1 bar. It should be maintained for any gas. Concentration will be 1 mole per dm cube for aqueous ions or species. Okay, yeah. So good to know the definition over here. Commit it to memory. The standard electrode potential of a half cell is the potential difference between the half cell and SHE or standard hydrogen electrode at standard condition of 298 Kelvin 1 bar for gases, 1 mole per dm cube for solutions. Okay, so if you remember what I said earlier on, potential difference essentially is how much work can potentially be done by a circuit. Okay, so let's say I give you an example. Say we have a 1.5 volts battery. Okay, therefore it will have a potential difference of 1.5 volts between its negative and positive terminal. Yeah, that is the maximum it can have. Of course, depending on the operating temperature, etc., the voltage might be less than 1.5. Yeah, so if we are going to connect a wire between the two terminals, then there will exist so-called a pressure for the battery to force the electrons all in the same direction in the same path around the circuit. Yeah, so you can view voltage as the force, okay, which pushes electrons around a circuit, because without a voltage, the electrons in a wire will just move randomly in any direction. Yeah, so I will need a potential difference, or I will need a voltage in order to push the electrons from a higher to a lower potential. Okay, yeah, so the units here is volts. Okay, basically if you try to recall from physics, 1 volt is the force required to drive 1 coulomb, okay, of charge through a resistor of 1 ohm in 1 second. The volts fundamental units are joules. I mean, it's written as volts, but if you break it out, it can be written as joules per coulomb. Okay, if it'll be good for you to read a little bit more. If not, then I think we can you can just settle with what we have in the notes. I think that should be sufficient for A levels. Yep, okay, and then we will need a voltmeter with high resistance, but this is a given because a voltmeter need to have high resistance anyway. Yeah, so sometimes in a lab, if you are going to perform a related experiment, you'll be using a multimeter. Yeah. Okay. So why do we need a high resistance voltmeter? So that it allows very little current to flow through it, and therefore the potential difference is the highest possible. Yeah, so the highest possible potential difference, it is also known as the electromotive force, which is something I'm not sure if it should be introduced in H2, but I mean, since it's written here in your notes, then yeah, just take note of it. Do remember, or I mean, if you really want to search for the difference, electromotive force is not the same as potential difference. Yeah, just to take note of it. There is a difference between the two. Yeah. So EMF, or electromotive force, is actually defined as the characteristic of any energy source capable of driving electrical charge around a circuit. Okay, so that is like the maximum capable of driving around the circuit. Okay, then what is the difference between electromotive force and potential difference in that sense? Okay, so I think first of all, right, we need to know that the difference between electrode potential of two electrodes of an electrochemical cell where no current is drawn from the cell is known as the EMF of the cell. Okay, similar to what we were talking about earlier on. Okay, whereas the difference between the electrode potential of two electrodes when the cell is sending current through the circuit is known as the cell potential. So therefore, EMF is the maximum voltage that can be obtained from the cell, whereas potential difference of a cell is always less than the EMF of the cell. Okay, if you are confused about what was mentioned, I think you can just kind of skip this part, because again, not so crucial for H2, but good to know the difference. Okay, yeah, so being the standard hydrogen electrode, it is assigned to have an electrode potential of 0 volts, so anything is always measured against the standard hydrogen electrodes. Okay, so yep, so this is a basic setup when we are trying to measure the standard electrode potential of zinc 2 zinc half cell. Okay, so this is a setup which I think you have seen earlier on. So basically the one on the left is SHE, everything else standard condition. And then on the right is a zinc metal rods and 1 mole per DMQ of zinc 2. Okay, when you look at the voltmeter reading, it should read as negative 0.76 volts. Okay, and how are we going to measure the standard reduction potential of a non-metal? Okay, so we have the example here. Again, the left hand side is standard hydrogen electrode. On the right hand side, we have chlorine gas bubbling into a solution containing chlorides. Okay, then how are we going to measure the standard reduction potential of two cations, one oxidized form, one reduced form? For example, iron 3, iron 2. Okay, same thing. We have the standard hydrogen electrodes on the left, and then on the right, we have an inert metal electrode, in this case platinum, and then we'll have 1 mole per DMQ of iron 2 and 1 mole per DMQ of iron 3. Okay, yeah, and then understanding standard electrode potential. Yeah, so these values can be obtained from the data booklet. I think I have introduced to that to you in the very early on in our lectures. Okay, so you may just refer to it at your own free time. Okay, yeah, so the half, okay, maybe I can just showcase to you some of them. Yeah, so you notice that these half equations are written as a reduction equation. Yeah, because the species on the left is gaining electrons to be reduced to the species on the right. Okay, so because of that, they are also known as standard reduction potential or standard redox potential. But if you don't wish to remember so many names, you just remember them as standard electrode potential. I think that will be sufficient. Okay, then for example, you have a dichromate, chromium 3, standard reduction potential written as plus 1.33 volts. Okay, so that means that for the dichromate chromium 3 half cell, the reduction potential is 1.33 volts. Do take notes of this particular annotation. It is very important, and it is something, it is something which I really want students to learn how to write out. So meaning when you want to show the standard reduction potential of dichromate chromium 3, you should write it as the standard, which is this, a circle with a dash, and then the rest will be in subscript. Okay, Cr2O7 2 minus slash Cr3 plus. Okay, the oxidized form is on the left, the reduced form is on the right. Remember that. Okay, yeah. I don't really like to talk about this particular point because some students will say, oh, if I reverse the thing, then I just reverse the sign. Yes, you're not wrong, but in most cases, the standards are written as standard reduction potential. We don't write them as standard oxidation potential. Just take note of it. Yeah, so this particular bullet points is just for your information, but they are not so commonly used. Okay, yeah, so as what you might have heard me earlier on, I stress upon the fact that fluorine is the strongest oxidizing agent known to mankind. Yeah, so in that sense, the standard electrode potential is a measure of how favorable the floor reaction is. So 2.87 volts for fluorine fluoride half cell. Oh, sorry, it's here. Fluorine fluoride is the largest value that you can ever be obtained. Yeah, so that means that fluorine has a super great tendency to be reduced to fluoride. Yeah, so the more positive the reduction potential value is, the more favorable is the forward reduction half equation. Then the more negative it is, the more favorable is the backward oxidation equation. Okay, so that means that if you look at potassium plus potassium, negative 2.92 volts, so that means that potassium is a very reducing metal. That means that it has a super great tendency to be oxidized to potassium plus. That means very great tendency to donate its electrons to some other species. Okay, yeah. This is quite important, but I will not discuss it in detail over here. If we multiply the equation by a coefficient, let's say silver plus electrons to silver, the reduction potential value is 0.8 volts. If I multiply by 2, the value will not change. A lot of you will be asking, why is that the case? Okay, the reason is because standard electrode potential value are what we call intensive property. I'm not sure is this the first time you have heard of intensive properties, but for example, you have encountered them for many years. For example, density and concentration are known as intensive property. Okay, so what does it mean? For example, if I give you 100 cubic centimeters of a 1 mole per cube solution versus 1000 cubic centimeters of a 1 mole per cube solution, right? The concentration does not change regardless of whether I increase the volume from 100 to 1000, but the mass changes. Yeah, so therefore we say that concentration is an intensive property, but mass is an extensive property. Okay, and volume is also an extensive property. Yeah, which means the property depends on the size or the amount of substance present. Yeah, so intensive property does not depend on the amount. At this stage, you might be wondering why is standard reduction potential or standard electrode potential an intensive property? Where when chance arises, I will prove it to you, okay, through calculation, but we need to relate that back to the thermodynamic link with delta G, okay, and then we'll deal with that later on. Okay, yeah, so 2.4, okay, using E0 value to compare relative strengths of oxidizing and reducing agents. I have kind of mentioned that to you quite a few times. Okay, yeah, so if I'm going to arrange them, you notice that this is quite similar to your reactivity series, remember? Okay, so in your reactivity series, I do believe that in secondary school, your teacher had told you that hydrogen is here. Anything below hydrogen cannot react with the acids. The metal cannot react with the acid, right? Yeah, so true enough, copper is in your reactivity series, and then I think you have silver. And then I think in secondary school, you should have zinc and iron, and then maybe aluminium and magnesium and even potassium. Yeah, so these are the reactivity series. So the origin of the reactivity series has got to do with the standard electrode potential values. Okay, yeah, so this particular list is just having the values being written in a certain way to show you that as the standard reduction potential become more and more positive, the stronger is the oxidizing agent. And then as it becomes more and more negative, the stronger is its ability to reduce. Whose ability to reduce? The metal's ability to be reduced. I mean, to be for the metal itself, that means that the more negative the reduction potential of, let's say, potassium plus to potassium, that means that potassium has a very great tendency to be oxidized, and therefore very great tendency to act as a very good reducing agent, because it has a very great tendency to donate its electrons. Why is that the case? Because in the course of being oxidized, electrons has to be transferred. Yeah. Okay. Right. Yep. So I've mentioned some of these things, so I don't think I will need to go into details. Please do read them on your own and then be familiar with them. Okay. Then right now we will work on exercise 2.1. Okay. Yeah. So 2.1a, decide if each of the following statement is true or false. Okay. Bromine is more easily reduced than iodine. So again, we'll take a look at the data booklets. Okay, so bromine. So we need to find bromine. I'm going to use another color ink so that it's clearer. Maybe I can erase some of these things so that you do not be distracted. Okay, yep. Okay, okay, so bromine is over here. Yeah, so this bromine, bromine bromides. Yeah, reduction potential 1.07 volts. Iodine iodide is 0.54 volts. Okay, so here we can see that the bromine bromide reduction potential value is more positive than iodine iodide. Yeah, so therefore I would expect bromine to be more easily reduced, or it has a greater tendency to be reduced as compared to iodine. Okay, so this is true. Okay, barium is more easily or more readily oxidized than copper. Yeah, so I think even without referring to this, you will agree with me, but let's take a look. Yeah, so you notice that barium is negative 2.90 volts. Okay, but copper to copper, where is copper to copper? Yeah, copper to copper is 0.34 volts. So that means that because the value is much more negative than copper to copper, so therefore the reverse reaction, that means barium to barium 2 has a very strong tendency to occur. Yes, so yes, barium is more easily oxidized than copper, so this is true. Okay, bromine is a stronger oxidizing agent than iron 2. Okay, yeah, so again, how do we judge? If bromine is being reduced to bromides, that means that it gains electrons. Okay, so we are comparing with whether there is a greater tendency for iron 2 to gain electrons. Okay, so if you look at iron 2 over here, right, the reduction potential value is negative 0.44 volts. So that means that it does not have a very strong tendency to gain electrons because it has a negative standard reduction potential value. So therefore, bromine is a stronger oxidizing agent than iron. So this is also true. Okay, aluminium is a weaker reducing agent than chromium. Okay, is this true? Okay, so aluminium, okay, so Al3 plus and Al is negative 1.66 volts. Yeah. Okay, let me erase the other two first because it's a bit confusing now. Okay, then chromium to chromium. Okay, this is 0.91 volts. Okay, even if you want to look at chromium 3, chromium is also negative 0.74 volts. Yeah, so which is more negative? So it's aluminium 3, aluminium is more negative as compared to chromium 2, chromium and chromium 3, chromium. Yeah, more negative means that the metal itself or the reduced form is a stronger reducing agent. So therefore, aluminium is a stronger reducing agent than chromium. So this is incorrect. So this is false. Okay. It is easier to reduce chromium 2 than to oxidize it. Okay, so same thing. We look at chromium 2. Okay, so let us see what are the information we need. We need the reduction reduction potential of chromium to chromium. So this is reduce chromium 2 to chromium. It's negative 0.91 volts. Okay, and then chromium 3, chromium 2 is 0.41 volts. Okay, so is this true? Is it easier to reduce chromium 2 to chromium, which is a negative 0.91 volts, versus is it easier to oxidize chromium 2 to chromium 3? Okay, yeah, because this value is negative in the forward direction, so therefore the reverse direction means that chromium 3 is thermodynamically more stable than chromium 2. Yeah, so therefore it is actually more difficult to reduce chromium 2. It's actually easier to oxidize chromium 2 to chromium 3 because chromium 3 is the more thermodynamically stable form. Yeah, so in this case, therefore, this is false. Okay, reducing power is in the order chloride, lead, aluminium. Okay, so let's see whether is it a correct. Okay, so maybe let me just erase all this first, because if not. Okay, so reducing power is in the order chloride. Okay, so lead and aluminium. Okay, so aluminium, as we saw, is definitely a very strong reducing agent because it has a very negative electrode potential. Yeah. So where is lead? Lead. Okay, so I think we need to erase some of these things first. Okay, lead. It's PB over here. Yeah. We're looking at lead. Okay, so lead over here. Yeah, you notice that the reduction potential of lead is very close to 0. So therefore, lead is not a very strong reducing agent. Yeah, so it should be aluminium greater than lead, right? Yeah, so in this case, the order is already incorrect over here. Okay, then if we look at chlorine chloride is a whopping 1.36 volts. Yeah, so therefore chloride is a very weak reducing agent in that sense. Yeah, so therefore this is definitely false. It's incorrect. Yeah, we can already tell it's incorrect simply by looking at lead and aluminium. It's already in the wrong order. Okay, so among the species given a list, which is the strongest oxidizing agents? Okay, so the list I do believe is based on the is based on this particular list. Yeah, I think we have earlier on already established fluorine is the strongest oxidizing agent. Okay, so we said fluorine, the strongest reducing agent. Remember earlier on I kept talking about potassium plus potassium, right? But it is definitely not the potassium is definitely not the strongest reducing agent. Okay, if you just scroll through, right? Did you notice something more negative? Is it sodium? No, not sodium. Okay, let me go up further. It's lithium. Okay, so lithium is even more negative than potassium plus potassium. Yeah, so therefore the strongest reducing agent is lithium. Okay, so which species can act as both oxidizing and reducing agent? I think there are many you can see. Okay, so for example, a classic example will be H2O2, which you are quite familiar with from titration. Okay, so in this case, the H2O2 here, itself being reduced, right? So therefore, it's behaving as an oxidizing agent. Okay, and let's see, and over here, oxygen is being reduced to H2O2, so H2O2 is being oxidized to O2, so therefore, because H2O2 is being oxidized, it is behaving as a reducing agent. Yeah, so in this case, H2O2, because there are separate equations where it appears on the left and right, it can appear, or it can behave as both an oxidizing and reducing agent. We will discuss more regarding the various values over here, because some of the values are quite confusing for students. Okay, so yeah, I think I will have a separate videos on that so that it's clearer for you guys. Another one which I think we can think of will be chromium, because remember earlier on we saw chromium on both sides. Yeah, so chromium in this sense, potentially it can behave as a reducing agent. Yeah, because it can be oxidized, or it can be an oxidizing agent, because it can gain something and be reduced to chromium. But obviously it will need a much more powerful reducing agent for it to act as an oxidizing agent. Yeah, okay, so yep, I think that's it. Okay, okay, so maybe let me write it down first. H2O2, okay, and maybe chromium 2+. Okay, in case some of you don't know how to see it, right, I will use the classic example of H2O2 here, so that it's easier for you guys to tell the difference lah. Okay, so first of all, right, I think we need to look at the position of H2O2. If H2O2 is written on the left of the equation, after the reaction it gets reduced to the species on the right. Yeah, so if it gets reduced, right, yeah, so that means that it behaves as an oxidizing agent. Okay, so behave as oxidizing agents. Why is it that when it gets reduced, it behaves as an oxidizing agent? Okay, so remember, what is the purpose of an oxidizing agent? The purpose is to oxidize its counterparts. In order to oxidize its counterparts, it needs to be desperate for electrons. It needs to take electrons from the counterparts so that its counterpart's oxidation state will increase. If it takes electrons from its counterpart, then itself has to be reduced, right? Correct or not? So oxidizing agents itself reduced. But if it's written on the left, in the half equation, it behaves as an oxidizing agent. Yeah. Then same case goes for H2O2. If it's written on the right hand side, it behaves as a reducing agent. Yeah. So what is the purpose of reducing agents? A reducing agent's role, right, is to donate electrons. Yeah. So once H2O2 donates electrons, itself gets oxidized, and then its counterparts gets reduced. Yeah. So I think you need to be very clear what you're saying and how you're writing it. But most importantly, I think it does help if you look at where the electrons are. Yeah. So therefore, an oxidizing agent accepts electrons, a reducing agent gives out electrons. Yeah. So if you are able to locate the position of the electrons, I think it will help a lot. Yeah. So same case goes for our earlier example on chromium. Yeah. So in this case, right, chromium 2 to chromium, right, the chromium 2 behave as an oxidizing agent. Yeah, because an oxidizing agent, as I mentioned, it's desperate for electrons so that it can oxidize its counterparts. Yeah, so therefore it accepts electrons. And then in this case, chromium 2 on the right hand side, it behaves as a reducing agent. Yeah, because it needs to donate electrons to its counterparts. So in order for it to donate electrons to its counterparts, right, it needs to be a reducing agent, or its counterpart needs to be a strong oxidizing agent so that chromium 2 can be oxidized to chromium 3. Yeah, so I think you need to see some of this logic clearly so that you won't be very confused in terms of doing the question and then to reason out things yourself. Okay, so I think at this stage you have sort of realized what may be a potential problem when you are working on electrochem and its potential difficulty as well. Okay, yeah. So with that, I think I have come to the end of the first segment on electrochem. Yeah, so please look out for the second segment where I will be discussing section 3 and 4 in some details.